Hi, everybody. So let's go ahead and talk about how heat and salinity impact ocean movement and just generally talk about ocean movement. So, ocean water is constantly being moved around. Okay, wind produces waves and surface currents, and that basically moves most of the surface water. Okay, but there are also density differences that create that deep ocean movement. We've talked about how density means like heavy dense water goes to the bottom of the ocean and low dense water goes to the top. So these density differences of the, you know, like top water and the bottom water create that circulation. Now, the moon makes the tides go in and out, and we're going to talk about that in a bit. So, surface currents are movements of water that flow horizontally in the upper part of the ocean surface. Okay, so the top part of the ocean moving because of typically wind. All right, these surface currents develop because of the friction between the ocean and the wind that blows across it. Now, some of these are local or seasonal currents. They're really small, they're often temporary, while others are permanent and they can extend over large areas of ocean. Now, this is related to the general circulation pattern of the atmosphere. So, if you remember for weather and climate about how the heat rises and then moves up to the poles and then it sinks and it comes back down, that kind of circulation pattern. Okay, so these surface currents are related to the pattern of wind. Now, there are huge circular moving current systems that dominate the surface of the oceans. These are what we call gyres, okay? They're large whirls of water within an ocean basin. So there are a few main ones. There's the North Pacific Gyre, the South Pacific Gyre, the North Atlantic and the South Atlantic gyres, and the Indian Ocean gyre. Okay. And these all sort of operate and move water across our oceans in a really big way. They kind of do some of that massive movement. The wind and the Coriolis effect deflects these currents away from their original course because of Earth's rotation, and that basically creates and directs the currents. Essentially, it's that combination. The wind makes the current move, it generates it, and then the Coriolis directs it slightly off center. So instead of going straight, the currents in the northern hemisphere are deflected to the right, and the currents in the southern hemisphere are deflected to the left, just like we were talking about with the wind. Okay, so if you take a look at this map, it really illustrates the different winds. So first of all, to read it, the warm waters are in red, and the cold waters are in blue. So notice that the cold waters generally go north to south in the northern hemisphere, and from the south to the north in the southern hemisphere. Warm water is the opposite. In the north, it's going from the south to the north, so from the tropics to the poles, and in the south, it's going from the tropics to the poles, but it's going from north to south, basically. It's going downwards, okay? Now, I'm going to point out the gyres here. So we have the North Atlantic gyre, which is basically like the east coast of the United States, Europe, West Africa, and we have the South Atlantic gyre, which is South America and Africa. Then here on the right, we have the Indian Ocean gyre, which is again in the Indian Ocean between Africa, India, and Asia and Australia. And then the Pacific Ocean gyre is a little hard to see because this is a flat map, but it basically operates between California and the west coast of the United States, and it then comes over here to this side to Asia, up through like around Japan and Russia, and then it comes back. So that's the North Pacific gyre. Okay, obviously, if the globe was round, you would see it, and I have another photo later that's going to like show that. And then you have the South Pacific gyre, which goes via Australia and then up via Peru and South America. Okay. And so basically, the only other thing here is that there is a current that kind of wanders around Greenland right here that's a little small. You have a Norwegian current up in the Arctic. And then in the south, in the Atlantic area, you have like this west wind and east wind drift. And we won't talk about that, but it is something to note that is there. Okay, so here is that picture of the Pacific, just because, the globe is actually round, and so you couldn't really see it before. So here's like a picture of that North Pacific gyre. So we have the gyre that basically goes from the south of California across the equator. It's called the North Equatorial. And then it goes up via Japan. That's why this part is called the Kuroshiro. And then up over the North Pacific area right here, past the Bering Strait, and back down the west coast of the United States. So within each gyre are four main currents. Okay, so typically each gyre has around four currents within it. All right, the North Pacific gyre has the North Equatorial Current, the Kuroshio Current, the North Pacific Current, and the California Current. Okay, if an object was to like start at LA, right, and we were to float an object into this gyre and then let it make its own way around this full loop, it would take it 6 years to get back to LA. Now, the ocean currents that affect climates, so ocean currents affect climates. So currents from low latitude regions like the tropics move to higher latitudes and they transfer heat from warm to cool areas, just like wind, just like the atmosphere, just like we were talking about in weather and climate. Like, for example, the Gulf Stream, which is here, it brings warm water to the North Atlantic current, like right up here. Okay, and that basically makes the Great Britain and Western Europe warmer in the winter than would be typical for the latitude, because technically Europe is at the same like latitude as like Greenland and Alaska, and it would be really really cold. It's like it's up where Canada is, right? So why it doesn't like freeze over all year round? Well, that's because it's getting that warm water from the Gulf. Okay. Uh, this is also why, like, the East Coast of the United States tends to be really cold, while the West Coast tends to be a little bit warmer, because the West Coast gets this lovely little gyre right here that brings warm water down, whereas on the East Coast, it's getting this cool gyre right here. So, warm ocean currents are felt mostly in the mid latitudes in winter. Okay, we can see that change in the temperature. It's just warmer in the winter in those areas that receive warm ocean currents. In the summer in mid latitudes, like Great Britain and stuff like that, you can feel those. Or sorry, in like the New York areas, you can feel that cold current. It's a little bit cooler in the summer times, and they're mostly felt in the tropics. Like you feel that as well. So the air from these cold currents begins in the cold high latitude region. So if you look here, it starts up in like the Greenland area, for example. Okay, as the cold current travels to the equator, they moderate the warm temps. That is, they reduce the heat of the warm temps. So, like California, for example, the California current helps cool us. Okay, because you have this cool water coming up and then the warm water coming down, but we get like a cool stream, like from this cool thing coming up this way, right? And so that cooler water helps cool LA during the summer. We get slightly cooler weather than like the interior of LA, like like Lancaster, Palmdale is warmer than, for example, the coast is. Now, ocean water movement does 25 of that heat transportation of the planet, while wind does the other 75%. So that's why when we're focusing on the atmosphere, we were really focusing on the wind and how that moved around heat, just because that was related to it. Now, upwelling is the rising of cold water from deeper layers to replace warmer surface water. Okay, so essentially, this is a wind induced vertical movement of water. So it comes from the deep and comes up. Now, coastal upwelling is seen along the coast of California, Western South America, West Africa. It's basically how the coastal winds plus Coriolis effect move the surface water away from the shore. So essentially, what happens is wind comes along, it pushes the surface water away from the shore. So instead of going towards shore, it goes away, goes towards the ocean. Water underneath upwells. Basically, it comes to take the place of that surface water that's being pushed away. And because it's coming from underneath, it's bringing cooler and deeper water because it's bringing water from the deep part of the ocean, which is colder than the surface water. And it moves that up to the surface, which brings lower surface temps near that shore. Okay. So upwelling basically, it not only brings cooler water. You can see this here in the picture. It brings this cooler water, but it also brings nutrient rich water. So the plankton and stuff like that are in this area love that stuff because they get the nitrates and the phosphates, and this increases their growth and supports fish and other organisms. So that's why places off our coast, off the west coast, are really great for fishing because we have this lovely, rich upwelling that allows that to happen. Okay. So, deep ocean circulation also moves water vertically. All right. It's basically supposed to mix those deep water masses. Now, we have density currents, which are these vertical currents of ocean water that result from density differences in the water. So, remember that denser water is with colder temperature or high salinity. So, the more salt it has or the lower temperature it has, the more dense it is. Dense water sinks, okay, and then it slowly spreads out beneath the surface. Now, how this whole thing works. So, cold water starts at high latitudes, okay? And it becomes, well, warmer-ish or warm-ish water becomes cold at the high latitudes, right? And the salinity increases because at those high latitudes we have sea ice forming when the polar ice caps were frozen, and sea ice forms and removes water from the equation, so the water becomes more salty. Now, when that water is dense enough, it's cold and salty and it's dense, it sinks to the bottom of the ocean and it starts these density currents. Now, once the water sinks, the density, the temperature, and the salinity stays the same as it moves across the ocean, okay? Because it stays deep and in the bottom of the ocean, and it doesn't get any warmer, it doesn't get any fresher or less salty, it doesn't get any less dense. It just keeps staying the same way as it moves across the world underneath in this bottom of the current, okay? And after sinking from the surface, these waters don't actually reappear at the surface for like 500 to 2,000 years. So it's for a really long time that this water gets stuck there. Okay. And so once it's cold and it moves down, it basically sinks, crosses most of the earth until it gets to an area where it starts to rise again and it starts to warm. But otherwise, it can just stay there pretty much for 500 to 2,000 years until it gets to that point. And then once it hits the tropics, it begins to warm and then it flows back through this little ribbony thing. They call it the conveyor belt, this picture thing. So density currents can also come from increasing the salinity of the water, right? So if you increase the saltiness when water evaporates. Now in the Mediterranean Sea, the salinity of that sea is 38 parts per thousand, okay, or 3.8%. Remember that? So this Mediterranean Sea forms dense water mass at the surface that then sinks and it flows into the Atlantic Ocean. So that's over here, right? Sinks, flows into the Atlantic Ocean. Now, this water is denser than the Atlantic Ocean water, right? The Atlantic Ocean surface water is 35 parts per thousand. So the Mediterranean Sea water is denser, so it sinks and goes underneath the Atlantic Ocean water. Now, as water then flows to the poles, because remember, the North Atlantic is going up towards the poles. As it flows to the poles, it cools and the salinity increases. It gets more salty, which makes it even more dense. And it goes back to the equator when it cycles back down as cold, deep water that eventually upwells, it rises, and as it warms and becomes fresher, it becomes less dense and then flows back up to the north where it cools and gets more dense. So that's basically how the ocean currents move around and they transfer heat and they do all the things. Now, water is a great conductor of waves and energy, and it can transfer energy like from a storm that's several kilometers, 1,000 kilometers away, and it can pass that wave energy through the water from like that far away location. It doesn't move the actual water molecules. It like the water molecules don't move from thousands of kilometers away to like right here. It's the energy from the storm can hit the water and sort of force, like with the wind, right? The wind hits the water, forces this wave energy through the water. And so even like where we are, we can see it in the waves. We not feel it, but we can see the waves rippling with that energy. Okay. It's basically like having somebody, like in our classroom, have a glass of water at one end and have somebody at the other end jump. Like, we can feel it. We can hear it and we can kind of see it and feel it, but like you can see the ripples still happen in the water because that like wave energy is still happening. So most waves obtain their energy and motion from wind, right? The stronger the wind, the bigger the waves. So crest is the top of the wave. So it's like right here at the top of this wave, that's the crest. Between two crests is the trough. So that's basically when the water is kind of like settled, it's kind of sunk. The wave height is the crest minus the trough height. So it's from the crest to the bottom of the trough. That's what we call the wave height. The wavelength is from crest to crest, or if you want to calculate it, from trough to trough. Okay, but it's basically the distance between two waves. Um, the time it takes for one full wave to pass a fixed position is called the wave period. Okay, so it's basically like if you have like a stop sign and then you move the wave across and like to go to the next point, like yeah, it's yeah, it's however long it takes for a wave to go past a certain position. So the height, length, and period of a wave depend on three factors: the wind speed, the length of time the wind is blown, and the fetch. That's the distance the wind has traveled across open water. Basically, the more energy there is, the higher and the steeper your waves are going to be. And when the waves grow so tall that they topple over, that's what we call white caps. Okay, you can see them in the picture. Now, wave energy can travel thousands of kilometers, right? It's not actually the water, but the wave energy. Now, there's something called the circular orbital motion. This is basically when water particles pass their energy along by moving in a circle. It allows the energy to move forward through the water while the individual particles are just moving around in a circle. So, this is basically how energy passes through waves and through water. Okay. Now, wave energy kind of does go downwards. Like, it's not just physically horizontal, it does go a little bit downwards. But the circular motion of those particles basically makes the energy like kind of just collapse underneath water. So we really only see the effect horizontally because when it goes downwards vertically, it just sort of fizzles out. There's not enough like movement to keep it going. Now, when a wave is in deep water, it's unaffected by water depth. So when you're talking about energy out in the middle of the ocean, you're not really going to see any huge waves because it's just out, like there's plenty of water underneath it to support that wave. Okay. But as that water gets closer to the shore, the water depth decreases. And basically, the water depth, as it decreases, forces the wavelength of the wave to decrease. It slows down the wave. Okay. And as a result, kind of like when the wavelength decreases and the wave slows down, it forces the height to go up. Okay. It's like a pressure pushing the height up. And so when the wave gets taller, um, the wave eventually becomes too steep to support itself. And so then it collapses on itself. And that's what we call a surf. Okay. That's what we call like actual waves. That's what the waves we see on the coast. All right. So the calculation to really figure out when you're going to start to see waves is when the water depth is half of the wavelength. Okay. So if the wavelength is like 30, then the water depth can't be any, like, I guess, larger than 15. If it's larger than 15, you're not going to see waves. But if it's less than 15, then you will start to see waves. Okay. Yeah. So, basically, if there's not enough water underneath to support the wave, and like especially the wave's height, it's going to collapse and it's going to break on itself and it's going to basically create a wave. Now, the water that then kind of goes up the beach from that, like, you have a big crash of a wave out in the coast, thing, people are surfing and everything like that, and then you have those tides that come up, right? You got the water that's coming up, you come and walk in the water. That like wash, that thing is called the swash. It moves up. Okay. Moves up the beach. And then when it comes back down the beach, like in the GIF, it is backwash. All right. So Another word for backwash. All right. So the tides. The tides are the daily changes in elevation of the ocean surface. Essentially, this is like think of it as how far the water is going to come up on the beach. Okay. When it's high tide, the water is going to come all the way up to the as far as it can go on the shore. When it's low tide, the waves don't go up as high. They, kind of stay closer to the body of the ocean. Now, ocean tides are the result of the gravitational attraction exerted upon the Earth by the moon and, to a lesser extent, the sun. Okay, most of our waves are created by the moon, but there is some effect that the sun does have. So, for example, if our moon were to disappear, we would still have some waves, but they really would not be anything significant. Like, for the most part, our seas would be calm. Okay. Like there'd be of course the effect of wind and our rotating earth and all of that kind of stuff. So we would see some waves. But in terms of like tides and stuff like that, we really wouldn't see them. Like the ocean would come to a certain point and then it would stop. We might see a slight change because of the sun, but it wouldn't be significant. Now, because the atmosphere and the ocean are fluid, the ocean's fluid, the atmosphere contains water vapor, right? And it's got clouds and stuff. Both of those things are free to move, okay? And so because of that, they are changed by that moon and sun gravitational force versus us, which are not fluid, and we therefore have the earth's gravitational pull pulling us down, and therefore we don't move with the moon and sun movement. Now, the moon mostly influences the tides, okay? The sun's effect is only about 46% of the moon's effect. The force that creates tides is gravity, and the force of the moon's gravity is stronger on the side of the earth closest to it. Okay, so what happens is that wherever the moon is in its rotation around the earth, the side that's facing the moon, the one that's closest to the moon, is getting a slightly stronger gravitational pull. And it creates what we call the tidal bulge. So this is what we see in this first picture right here. Okay, there's a bulge that's edging slightly towards the moon. Okay, now, on the opposite side of Earth, water is pulled away from the moon, and it produces an equally large tidal bulge on that side of the Earth. So we see it on this side right here. Okay, the water on this side is pulled away from the moon. And so essentially what happens is that they even themselves out because we've got these two bulges on either side. So instead of having two like an egg-shaped tidal bulge, we basically have like an oval-shaped tidal bulge with two bulges on either side of the earth. Okay? So, because the moon doesn't shift much day to day, the bulges remain in place while the Earth rotates through them. So, basically, as we go into a bulge, the tide rises, and between the bulges, the tide falls. Okay? So here we have this thing where it's like, actually, that's for the next thing. I probably should put that picture on the next slide. But basically, if we go into a bulge, okay, like we're either going towards the moon on this side or we're going away from the moon on the opposite side. If we end up like in either of those spaces, we're in high tide. And then if we're in a place where we're like in between, so we're on like the Americas side in this picture, or on the opposite side of the planet, we're in low tide. Okay. So the sun produces smaller tidal bulges on the Earth too. The most noticeable effect is during the new and the full moons. So that's when the sun and the moon are aligned, and therefore the forces are added together. So in this picture, for example, okay, during the full moon or the new moon, the sun is in this direction. So there's a straight line that you can draw between the moon, the sun, and the Earth. Okay, it's like if it's the full moon, then the moon is on the opposite side of the earth from the sun, but you can still draw a straight line through them. Or the new moon, it's like on the same side as the sun, so you can draw a straight line through them. In that case, you're going to have the combined gravity of the earth of the moon and the sun is going to create larger tidal bulges. Basically, it means that your high tides are going to be higher and your low tides are going to be lower. All right. Now, the tidal range is the difference between those highs and low tides. And the spring tide basically is saying we're going to have the greatest tidal range. So, for example, if your tidal bulges, your higher tides are like, you know, I don't know, like 10 feet above sea level, and then your low tide is like 1 foot above sea level. Okay. And that's your, new moon, full moon situation versus like, um, 7 feet above sea level for the high tides at normal time and 3 feet in the low tide. Like your tidal bulge, like 7 minus 3 is 4. So that's typically on average what you would have for your tidal difference. In a new or full moon situation, you're having a greater difference of like 10 minus 1. So that's 9. Okay. It's basically the idea is you're going to have a bigger tidal range during the full moon and the new moon because you're going to have lower tides, lower low tides, and higher high tides. And spring tides are what those things are called. Now, during the first and the third quarters of the moon, okay, so when the moon is on opposite ends of the earth and it's at 90 degrees to the sun, you basically are having a situation where the moon and the sun are offsetting each other. Okay. So they're basically kind of negating their own gravitational forces. So when it's kind of like this, where it's like an L shape instead of a straight line, you're basically going to see very small tidal ranges. It's what we call a neap tide. Okay. Your low tides and your high tides are going to be really similar. They're going to be very close together. And this tends to happen on the first and the third quarters of the moon when it's at basically a right angle to the sun. All right. So tides at various locations respond differently to, this moon, sun, earth effect kind of thing. Okay. And these changes can be based on the coastline, the shape of the ocean basins, the water depth, a whole bunch of stuff. There are three different patterns that we see with tides. Some places have diurnal tides, which basically are one high tide and one low tide every day. The semi-diurnal tides are 2 high tides and 2 low tides per day. And the high tides and the low tides are the same height. So you can see that here, where it's like you got basically it's 4 tides a day, 2 high, 2 low, and the heights are the same. The mixed tidal pattern is when you have 2 high tides and 2 low tides per day, but the tides are at different heights. And so that's demonstrated in this picture right here. Okay. And that's basically it. It's just, I wanted to point out that these patterns exist, that we do see them happen, and that, yeah, they're based on all kinds of shapes and stuff like that. But we don't need to go into the terrible details of that. So that's it for today's notes. I know it's relatively short compared to what we normally do, but we will kind of pick up talking about, the coast and shores and oceans and stuff like that in the next week's assignments. Okay? Thank you so much, guys. Have a good one. Bye bye.